Let us now discuss the series RLC circuit, where we will find out the resonant frequency, the current, power, and also some more very important parameters. Okay. So, we have the AC source, resistance and an inductor capacitor in series. So, the voltage source we will take as having a magnitude Vm, angle theta. So, we have taken Vm here, that means the maximum value. You can take the RMS value as well. Okay. Magnitude can be either in terms of maximum value or in terms of RMS value. If nothing is mentioned, we take it as, we consider the magnitude to be the RMS value. And these parameters we will take R, L and C. Now, what will be the resonant frequency? This is same as what we have previously derived. Okay. Omega R is equal to 1 by root LC. How did we get this? By equating XL is equal to XC. So, what will be the resonant frequency in hertz? 1 by 2 pi root LC. Okay. So, resonant frequency, it will also be sometimes represented as omega naught in some textbooks. So, both of them, they mean the resonant frequency. F naught is the resonant frequency in hertz. So, you can write the units here. This is in radian per second and this is in hertz. Now, what will be the current? The current I, the phasor I, will be simply equal to the voltage phasor divided by the resistance, because the reactance is 0. So, what will be the magnitude of current I? The magnitude, that is mod I bar, is equal to Vm by R. Okay. And the current in terms of phasor, it will be Vm by R will be the magnitude and angle will be theta, that is in phase with the voltage. Now, what about the power? Now, the power, if you write in terms of the maximum values, what will be the half into Vm into Im cos phi. Okay. Where phi is the phase difference between voltage and current. How much is the phase difference? It is 0. So, cos phi will be 1. Now, Im, if you write in terms of the voltage Vm by R, what will you get the answer? Vm square by 2R. So, this is when in terms of the maximum values. If you want to express in terms of RMS value, then Vm is going to be root 2 times the RMS value. So, the final expression you are going to get V RMS square divided by R. This is in terms of RMS values. And remember that this power is the maximum power that can be dissipated. Okay. So, you can write here maximum power is dissipated at resonance condition. Let us now draw the phasor diagram. So, in the phasor diagram, we will be representing the voltage as well as the currents through each of the elements. So, the source voltage, what will it be? Let us take the source voltage if you take as Vs. Then this will be equal to the voltage drop across the resistance plus the voltage drop across the inductance plus the voltage drop across capacitance. Okay. Now, this VL and VC, they will cancel out and Vs will be equal to Vr at resonance. Okay. At resonance, VL will be equal to Vc. Here the magnitudes, not the phasor but the magnitudes. The phase will be opposite, that means VL bar plus Vc bar is equal to 0. This is why, because the current is same, because it is a series circuit and the reactances are same. So, the voltage will be same. So, VL is equal to Vc and so Vs will be equal to Vr. So, what will be the phasor diagram? This will be Vs is equal to Vr. The current will be somewhere here. This is equal to, these are all phasors. Okay, talking about the phasors. So, this will be equal to V bar by R. Now, what about VL? VL is going to be leading the current. Okay, see the current phasor is here and the voltage phasor is leading, because in the inductor the voltage will lead current by 90 degrees, because VL is equal to j omega L into current. What about VC? VC will be ekdam opposite, right, and both these magnitudes will be equal, so that Vs, you will, when you add VR plus VL plus VC, when you add, you will simply get Vs is equal to VR. So this is the basic parameters that we have seen here, but there are some additional parameters that we will be using in resonance. The first parameter is the half power frequency. So what is this half power frequency? We have seen that the maximum power will be dissipated at resonance condition, right? Now we require the frequency at which the power dissipated is half of the maximum power, okay? Frequency at which power dissipated is half the maximum power. That means power dissipation at resonance. So the power, maximum power, we have already found out in terms of the maximum values of voltage and current. What will it be? Vm square by 2R, or you can also take the RMS values, V RMS square by R. Then what will be the power at half power frequency? We will take this as PH, okay. So this is going to be P max by 2, which is equal to how much? Vm square by 4R. But the average power, the real power, we can write in terms of the current as how much? Half Im square into R. From here you can express the value of current in terms of the voltage. You are going to get Vm by root 2R. So that means at half power condition, the voltage is related to the current is related to the voltage in this manner. So from here you can get the value of impedance. What will be impedance? Mod Z is going to be equal to Vm by Im, which is equal to root 2 times R. So at half power frequency, the impedance value is equal to root 2 times the resistance value. Using this relation, you can get the expression for half power frequency, right? So finally we want to find out the half power frequency. You will see that you will get two half power frequencies, okay. So we will see what that is. Mod Z is going to be equal to root over R square plus XL minus XC whole square. So this is equal to, this is root 2 times R, right? So root 2 times R. So if you square on both sides, then you are going to get R square plus XL, you will write as omega L, minus XC will be 1 by omega C whole square. This is equal to 2 R square. Further, if you simplify, you are going to get omega L minus 1 by omega C is equal to plus or minus R, the resistance value, okay. So now you can get quadratic equations in terms of the frequency. You are not going to get just one but two. If you take plus R, then you will get one quadratic equation. If you take minus R, you will get another quadratic equation. So both the quadratic equations, if you write, you are going to get omega square plus omega R by L minus 1 by LC is equal to 0, and also omega square minus omega R by L minus 1 by LC is equal to 0, okay. So from this equation you will get the solution as minus R by L plus or minus root over R by L whole square plus 4 by LC divided by 2, okay. So if you divide the entire expression by 2, then you are going to get minus R by 2L plus or minus root over R by 2L whole square plus 1 by LC. Similarly, this equation you are going to get two equations. What are they? R by 2L plus or minus root over R by 2L whole square plus 1 by LC. Now you have four different values of frequency. But if you say carefully, the frequency will be a positive value, right? But here if this negative value is used, then this entire value will become negative. Similarly, here if you use the negative value, then this entire expression is going to also become negative. So taking only the positive values, taking only positive values, since frequency can only be positive. Okay. So what will you get? One equation will be omega 1 is equal to minus r by 2l plus root over r by 2l whole square plus 1 by LC, and omega 2 is equal to plus r by 2l plus root over r by 2l whole square plus 1 by LC. So we are taking one root from here and one root from here. Okay. The other two roots are going to be giving a negative value of frequency. Let us now draw the frequency response. So that means the parameter we are considering is the current I as a function of the frequency omega. What will be the expression of I? This is equal to Vm divided by, this is for the series RLC circuit. We are discussing about series RLC circuit. Okay. So Vm divided by the impedance, and impedance value is root over R square plus omega L minus 1 by omega C. This is the general expression. I am not talking about resonant frequency or half power frequency, but the general expression for current in terms of the voltage and the frequency R, L and C parameters. Now if you put various values of frequency here, then you will get various values of I. That is what we are plotting here in the I versus omega graph. Okay, so this is called as the frequency response. So this will come out to be something like this. It will go to a maximum and then it will start coming down. So where will the maximum value occur? This current will be maximum when the resonant condition is achieved. That is at resonant frequency. Now where will the half power frequencies be? So we know that at half power frequency, we have found the expression for Im to be equal to Vm by root 2R. What about at resonance? At resonance, Im is equal to Vm by R. So somewhere here let us say this is Vm by R. So somewhere here it will be Vm by root 2R. So the half power frequency, one half power frequency will be here. This is omega 1, and another half power frequency will be beyond the resonant frequency. What is the expression of this frequency? This is minus r by 2l plus this expression. Omega 2 will be greater than omega 1 because here you have plus r by 2l. So it will in fact be greater than the resonant frequency as well, because resonant frequency is simply 1 by root LC. Now there is a very important formula which relates the resonant frequency and the half power frequencies. Okay. So what is that? The resonant frequency omega r is the geometric mean of the half power frequencies. That means root over omega 1 omega 2. Resonant frequency is geometric mean of half power frequencies. So what is meant by geometric mean? It comes from a geometric progression. So what is a geometric progression? We abbreviate as GP. So this is A, AR, AR square, AR cube and so on. So you can see that each number is being multiplied by a common number. So A into R gives you AR. Further if you multiply by R, you will get AR square, AR cube and so on. So what will be the geometric mean? So this AR if you take, AR is the geometric mean of the just before number and just after number, because you can get it as root over, let us say take this to be some B1 and this is B2. Root over B1 and B2 will give you what? Root over A into AR square. So this is simply AR, which is the number in between both of them. Okay. So similarly, this geometric mean omega r is the geometric mean of omega 1 and omega 2, implies that omega 1, omega r and omega 2, they are in a geometric progression in this order. The next important parameter is the bandwidth. Bandwidth is the difference between the half power frequencies. So we will write bandwidth is equal to omega 2 minus omega 1. Omega 2 is greater than omega 1. Okay. Now if you substitute the expression for omega 2 and omega 1, okay. So let me write it for you here. R by 2L plus root over R by 2L whole square plus 1 by LC will be omega 2 minus of minus R by 2L plus root over R by 2L whole square plus 1 by LC. Okay. So what will you be left out with? You will be left out with 2 times R by 2L, that is R by L. So this is the expression for the bandwidth for, remember which circuit we are talking about? The series RLC circuit. Okay. This is the general expression, okay, irrespective of the kind of circuit. This is the specific expression for the series RLC circuit. Another important parameter is the quality factor. So the quality factor is defined as 2 pi times the ratio of maximum energy stored in the circuit divided by the total energy lost in one time period at resonance. Okay. So using quality factor, we will get an idea as to how much energy a circuit can store in proportion to the energy that it can dissipate. Okay. So you can see what will be the maximum energy stored in the circuit. Energy storage can be done only either by a capacitor or inductor, right? These are the only two energy storage elements. Now when will maximum energy be stored in the circuit? If you consider the inductor, the energy storage is given by half Li square, where the current is the current flowing through the inductor at that point, right? Now when will this value be maximum? When the current is maximum. And when will the current be maximum? The current will be maximum under resonance condition. So the maximum energy will be stored in the circuit at resonance condition. Okay. So we can write, now we can find the expression for the quality factor. 2 pi times half Lim square, this is the energy, divided by total energy dissipated in one time period, we can write as the power into time. So what will be the power that will be dissipated? Half Im square R into the time period is given by TR. Okay. So this is power and TR is the time. Power into time will give you energy. Okay. So here we can take the expression for this energy stored in the capacitor, that means half CV square. But in that case we cannot cancel the voltage. This is series circuit, so current we can cancel, voltage we cannot cancel. So that is why we are taking in terms of the energy stored in the inductor. Okay. So what will be the final expression? You are going to be left out with L by R into 2 pi by TR, but 2 pi by T is nothing but the angular frequency. So the final expression is going to be omega R L by R. This is the expression for quality factor in a series RLC circuit. We can also write this expression in terms of the capacitance. So how to write? We know that omega R square is equal to 1 by LC, right? So L you can write as 1 by omega R square C. So if you substitute that expression for L here, then you are going to get 1 by omega R C R. So this is the expression for quality factor for a series RLC circuit. Okay. Now quality factor is also regarded as a measure of the sharpness of resonance. Q is a measure of sharpness of resonance. So what does this sharpness mean? So this we will understand if you see the frequency response curve. We saw the frequency response curve previously, right? So now for the same, this is the omega R. A circuit can have the same resonant frequency but a different frequency response, something like this. You can see that the resonant frequency is same for both the circuits, but this is somewhat narrower. The frequency curve is somewhat narrower, whereas this green color is having a broader frequency curve. So now this circuit, which is more narrow, this is considered to have a higher quality factor, and this curve is said to have a lower quality factor. So this is a more broader frequency response. You can see that for the narrower curve, the magnitude of current is dropping off at a faster rate, right? But whereas for this, the drop in current with frequency is at a much smaller rate. So that is one way in which you can say differentiate between the different quality factors. So Q gives an idea as to the rate at which magnitude of current falls on either side of the resonance. Okay, because resonance is the peak. One more observation that you can see is the bandwidth. The bandwidth is the difference between the half power frequencies. Now for the lower quality factor, omega 1 is here, omega 2 is here. What about for the higher quality factor curve? So this is the maximum value now. The maximum value is changing. So the half power current also will be higher. At least it will be higher than this current. Okay. So the half power frequencies will somewhere be here. So you can see that for the broader curve, the bandwidth is here, and for the narrower curve, the bandwidth is here. Okay, so you can take it as bandwidth 2, bandwidth 1. Bandwidth 2 is lesser than bandwidth 1. So a narrow curve means that it just means that bandwidth is less. Okay, so bandwidth is lesser for higher quality factor or for the narrower curve. Basically the higher quality factor curve, it is more selective. Okay, so that means you will understand more when we discuss filters. It will respond to a certain frequencies and it will reject all other frequencies. That is the importance of higher quality factor. Okay, so you can write that as well. Higher quality factor implies that it is a more selective circuit. Okay, so selective means ability to respond to certain frequencies and reject all other frequencies. So the one of the most practical applications that you can see is the tuning of your radio, right? So you want to tune to a certain frequency and you want to reject all other frequencies. What will happen if it is accepting more frequencies? Then more noise will be present. Okay, so that is the purpose of a higher quality factor circuit. Finally, one last topic here in the series RLC circuit is the relationship between the quality factor and bandwidth. We have seen the expression for bandwidth is equal to R by L, resistance by inductance. And what was the quality factor? This was the resonant frequency into inductance divided by R. So from here you can write omega R divided by bandwidth, because R by L is bandwidth. Okay. So what is the relationship? Q is equal to the resonant frequency divided by bandwidth.